Imagine a way to communicate that's unhackable, not just hard to break, but protected by the laws of physics themselves. That's the promise of quantum communication satellites. Today, we're diving into the top 10 breakthroughs that have taken us from theory to the brink of a quantum-powered internet. Let's dive into the fascinating world of quantum security. First up, we have quantum key distribution, often referred to as QKD. This is a cornerstone technology, a fundamental building block in the quest for truly secure communications. It represents the very foundation of quantum security, offering a radical departure from traditional cryptographic methods. It's a new paradigm in how we think about protecting our data. Unlike traditional encryption, which relies on complex mathematical algorithms that can be vulnerable to increasingly powerful computers, QKD takes a completely different approach. It uses the fundamental properties of photons, individual particles of light, to encode cryptographic keys. These keys are the secret codes needed to encrypt and decrypt messages. Now here's where it gets really interesting. If anyone, and we mean, tries to intercept these photons during transmission, the very act of observation fundamentally changes the photon's quantum state. This alteration doesn't go unnoticed. It immediately alerts both the sender and the receiver that something is amiss, that an eavesdropping attempt is in progress. This means that any attempt at eavesdropping is not only difficult, but it's also instantly detectable. The system is inherently self-aware of any intrusion. And the best part? If a potential breach is detected, the compromised keys are immediately discarded, rendering any intercepted information useless. So it's not just about making hacking more difficult or time-consuming. It's about making it fundamentally impossible to intercept the key without being detected, providing an unprecedented level of security. This isn't just clever engineering. It's all thanks to the fundamental laws of quantum physics, which govern the behavior of matter and energy at the atomic and subatomic levels. QKD is the driving force, the engine behind the development of quantum satellite networks, enabling secure communication across vast distances. This technology is enabling provable physics-based security, a level of assurance that traditional methods simply cannot match. Without QKD, the dream of an unhackable internet, a truly secure global communication network, would remain firmly in the realm of science fiction, a tantalizing but ultimately unattainable goal. It's the fundamental breakthrough, the core innovation that underpins virtually every other advancement in quantum security that we'll be exploring today. Next, the 2016 launch of China's MICUS satellite, the world's first quantum communication satellite. MICUS proved that fragile quantum signals could survive a journey from space to Earth, overcoming huge technical doubts. This wasn't just a scientific experiment, it was a bold leap that turned quantum communication into a global infrastructure project. Its success triggered a new space race, with countries worldwide accelerating their own quantum satellite programs. MICUS was the hardware breakthrough that made global quantum communication possible. It set the stage for every satellite-based advance that followed. The third breakthrough, a monumental achievement in quantum communication, involved actually connecting satellites to ground stations using quantum signals. This wasn't just theoretical, it was a practical demonstration of quantum key distribution over vast distances. The implications of this are enormous, paving the way for ultra-secure communication networks that are virtually unhackable. To achieve this, MICUS, the quantum satellite, had to send single photons from orbit, a feat of incredible precision. These photons, the fundamental units of light, were directed to a tiny telescope on Earth, requiring pinpoint accuracy. This was accomplished using a high-precision pointing and tracking system, a marvel of engineering that compensated for the satellite's movement and the Earth's rotation. In 2017, after years of dedicated research and development, MICUS successfully established stable quantum links. These links connected the satellite with ground stations over 1,000 kilometers apart, demonstrating the scalability of the technology. This groundbreaking achievement proved beyond any doubt that quantum keys could be transmitted securely from space to Earth. This was achieved despite the significant challenges posed by atmospheric turbulence and light pollution, factors that can easily disrupt delicate quantum signals. The team's engineering prowess, their innovative adaptive optics, their incredibly precise tracking mechanisms, and their robust, highly sensitive detectors all made this seemingly impossible feat possible. This successful demonstration was not just a scientific curiosity, it was the first real step toward building a practical, space-based quantum internet, a network that promises unparalleled security for global communications. It definitively showed that the core technology required for such a network could reliably work outside the controlled environment of a laboratory and function effectively in the challenging conditions of the real world. The satellite-to-ground link successfully turned complex theoretical concepts previously confined to research papers into tangible, secure data transmission, marking a significant leap forward in the field of quantum communications. Now for the mind-bending distributing quantum entanglement over vast distances. Entanglement links two particles so that measuring one instantly affects the other, no matter how far apart. MICIUS sent entangled photons to ground stations 1,200 kilometers apart, proving the spooky action survived the journey. This shattered previous distance records and showed that space-based entanglement is possible. Distributing entanglement is key for advanced quantum networks and future quantum repeaters. It's a critical step toward a truly global, secure quantum network. Space-made entanglement practical on a planetary scale. Breakthrough 5: Quantum teleportation. This isn't just theoretical physics anymore. It's a tangible achievement pushing the boundaries of what we thought was possible. We're entering an era where the seemingly impossible is becoming reality, thanks to the intricacies of quantum mechanics. Not of people, thankfully, but of information. Let's be clear, we're not beaming people across vast distances like in Star Trek. The quantum teleportation we're discussing deals with the transfer of quantum states, the very essence of information at the subatomic level. Scientists teleported the quantum state of a photon. This single photon, a particle of light, carried its unique quantum properties across a significant distance, showcasing the potential of this technology. From a ground station in Tibet, nestled high in the mountains, to the MICIUS satellite, a testament to human ingenuity in space, over 1,400 kilometers away. This remarkable feat demonstrates the ability to transmit quantum information across vast distances, opening up new possibilities for secure communication and distributed computing. This process destroys the original state. It's crucial to understand that the original photon's quantum information isn't simply copied, it's transferred. The original photon ceases to exist in its initial state and recreates it perfectly at the destination. The receiving photon, located over 1,000 kilometers away, instantly takes on the exact quantum characteristics of the original, as if it were the same particle, without the information physically traveling the distance. This is the magic of quantum teleportation, the instantaneous transfer of quantum information, leveraging the bizarre phenomenon of quantum entanglement. It's a fundamental building block for distributed quantum computing. Imagine a network of quantum computers, each capable of performing complex calculations and sharing information instantaneously through quantum teleportation and a quantum internet. This is the future of communication, a network where information can be transmitted securely and instantaneously across the globe. Teleportation allows quantum information to move securely, even across continents. Because the information isn't physically transmitted, it's inherently protected from eavesdropping, ensuring unparalleled security. In 2017, this sci-fi concept became reality, marking a pivotal moment in the history of quantum physics and paving the way for a new era of technological innovation. It enables quantum computers to link up, forming a powerful network capable of tackling problems that are currently beyond the reach of classical computers, and share information globally, fostering collaboration and accelerating scientific discovery on an unprecedented scale. Quantum teleportation is now a real-world tool, a testament to human curiosity and our relentless pursuit of knowledge, promising a future where the impossible becomes commonplace. The sixth breakthrough, building the first prototype global quantum network. Using MICIUS as a trusted relay, scientists linked satellite and fiber networks across thousands of kilometers. They even connected Beijing and Vienna, 7,600 kilometers apart, using quantum-secured keys. This hybrid network proved that quantum security could scale internationally. It's the blueprint for a future quantum internet, combining satellite reach with fiber connectivity, the first step toward a seamless, unhackable global web. The seventh breakthrough, overcoming Earth's atmosphere, the nemesis of quantum signals. Engineers built a network of ground stations, so if one was clouded over, another could connect. Adaptive optics on telescopes corrected for atmospheric turbulence in real time. Advanced filters blocked out background light, isolating the faint quantum signals. These solutions made quantum links reliable, not just fair weather experiments. Practical engineering turned a scientific marvel into robust infrastructure. Now, quantum communication works under real-world conditions. Eighth breakthrough: the first intercontinental video call secured by quantum keys. In 2017, leaders in Beijing and Vienna held a 30-minute video conference, encrypted with keys generated by Micius. Quantum key distribution enabled unbreakable, real-time communication. This wasn't just a demo, it proved quantum security could protect real-world applications. Sensitive conversations and financial data can now be shielded from interception. It was the hello world moment for global quantum security. Quantum tech moved from the lab to everyday use. Breakthrough 9: integrating quantum networks with existing internet infrastructure. Quantum and classical systems operate differently, but new protocols and quantum routers bridge the gap. Quantum networks generate tamper-proof keys, while classical networks handle high-speed data. This hybrid approach allows organizations to add quantum security without rebuilding everything. It's a practical, scalable way to roll out quantum protection worldwide. Integration makes quantum tech accessible and economically viable. It's the bridge to a quantum-secure future. The final breakthrough: global collaboration and the future of quantum communication. After Micius, countries worldwide launched their own quantum satellite programs. International partnerships are driving rapid progress and setting global standards. Next-gen satellites will be smaller, cheaper, and more capable, with quantum memory and repeaters. The vision: a constellation of quantum satellites providing continuous, unhackable coverage. The quantum revolution is now a global, collaborative effort. 10 breakthroughs have taken quantum communication from theory to orbit. This isn't just faster communication, it's a fundamental shift in digital security. The next decade will bring quantum satellite constellations and a true quantum internet. We're witnessing the birth of a new era in secure global communication. What excites you most about this technology? Let us know in the comments. Thanks for watching. Subscribe for more on the quantum revolution. Before you go, let's keep the momentum going. If you're fascinated by the future of quantum communication, hit that subscribe button and become part of our growing community. Like this video to show your support for the quantum revolution, and share it with friends who love cutting-edge tech. Got questions, ideas, or predictions about quantum internet? Drop them in the comments. We're excited to hear your thoughts and might feature them in future videos. Stay curious, stay connected, and don't miss our next deep dive into the world of quantum breakthroughs. See you in the next video. Subscribe, like, and comment below to support our channel and stay updated on the quantum revolution. Your engagement helps us bring you the latest breakthroughs and keeps our community thriving. Hit that subscribe button, give us a thumbs up, and share your thoughts in the comments. We can't wait to hear from you. Join us on this journey into the future of technology. Let's shape the quantum era together.